Resonance happens with light as well, the atoms that produce the light. And I've got here a laser. Many of you will be familiar with lasers. And this laser works on the principle of resonance of the light waves. Depends on the frequency of the light waves. And a laser, because you see with resonance, I can get a big movement from quite a small input. The same thing happens with my laser. I can get a very powerful light output from this tiny little thing. And I can get a very big, very concentrated, very powerful light output from this by just a very low energy input, but I'm making the input at the same frequency as the light waves. And this laser here is so powerful that it actually has to have a key to turn it on. And if I shine it up there, you can see I get a very, very bright spot of light. And this laser is so powerful, that it would shine on the mountain on the other side, a kilometer away, and I would be able to see the green spot on the mountainside. Well, lasers are not just for shining up onto a wall. It's the basis of how your DVD player works, how your CD player works. With a DVD, you've got your disc here, and a laser beam shines down onto it, and the light is reflected from the CD. And when we talk about light waves, I'll talk a little bit more about how a laser light gives us the picture and the sound that we get with a DVD. So resonance is the principle that lasers work on. I should add, incidentally, you must be very, very, very careful with lasers, because if this beam were to shine into your eye, it would make you go blind in that eye. Lasers produce very high power beams of light. If I were to shine my laser directly into the television camera, then I would destroy the little detector cell in the television camera, and BBS would not be very happy. So I won't. It's like a magic sword, isn't it? The natural frequency of oscillation of the mass and elastic band. If I try to make it move rapidly, not much effect. If I try to make it move slowly, not much effect. But if I try to make it move at its natural frequency, the thing vibrates a very great deal, and in fact, it would destroy itself. Now, I've got the mass there and the spring there. Just turn it upside down. The mass here and my hand down there. And what we have got is a car suspension system, the spring system on a car. Here's the car, a mass. Here's the car. And what's down here? Answer. The tires connected to the car body through springs. And as you go over the road, the tires are moving up and down. And they're making the car body move. Now, I'll just turn it back this way, and we have exactly the same effect as in a car. The tyres, if the tyres are going over a road and are made to bump up and down by the bumps on the road at the natural frequency of the spring car system, your car body bounces up and down with a very, very large amplitude, and it's very uncomfortable. But if you are going over a road and the tyres are vibrating rapidly, brrrr, like that, the car body hardly moves. So what this tells us is a rather strange fact. Sometimes, not always, but sometimes, if you're going over a bumpy road, it's better to go quicker rather than slower. And it'd be rather interesting to try that sometimes, but be very careful. This doesn't apply to a road where you get great big potholes in it. You try going quickly over potholes and you'll ruin your car and perhaps knock yourself off the road. But where you get regular bumps on a road, if you go slowly, you may be causing the tyres to bounce up and down. And remember, car tyre, there's the car, there's the tyres. You may be causing the car tyres to bump up and down at the natural frequency of your suspension system, and in which case the car body goes up and down a great deal. So let's just move from my padlock on the end of some elastic bands. Let's just go from there to see how this explains to us the basic principles of car suspension. Now, remember I said earlier, this is like the car suspension upside down. So I've actually downloaded from the internet, and I'll again remind you how really useful the internet can be for learning things, especially technical and scientific things. So I've downloaded this picture of a sort of a four-wheel drive going over a bumpy road. And it makes the point that going over a bumpy road can sometimes do a lot of damage to your motor car. Let's look to see how the suspension is affected by the bumpy road. Now, there's the car, the wheel, and the spring. As it goes over the bumpy road, you can see the wheel goes up and down, and the force is then transferred to the car body, which goes up and down. And this is the suspension of the vehicle. Now, let's see how this compares to my padlock and elastic band. I mentioned that padlock and elastic band is a bit like a car suspension upside down. I was doing this, but this is doing that. So my padlock was like the car body. Here we have the wheels going up and down because of the bumpy road, and the force is transmitted through the car suspension to the car body. So that is, in effect, the car suspension system. Now, depending on how fast I go, depends how often the wheel goes up and down on the bumpy road. And with this little animation from the internet, I can see the effect of going faster. As with all animations, they're very good. All I have to do is press the accelerator. Now look at the speed the wheel is going up and down, and look at the amount of movement of the car. Now I'm going to increase the speed. So the wheel is going to go up and down a bit faster, and eventually the wheel is going up and down at the natural frequency of vibration of the suspension system. And what happens to the movement of the car body? I increase the speed. You see the car body movement is getting bigger and bigger. And when I eventually am going sufficiently fast so that the wheel is going up and down at the natural frequency of the suspension system, then the movement of the car becomes very uncomfortable indeed. The natural frequency of the suspension system is now equal to the frequency with which the wheel is going up and down. But watch what happens if I go faster. You'd think if I go faster it would be worse, but watch. Going faster. And as I go faster, the movement of the car body gets less and less and less because the wheel is going up and down at a higher frequency than the natural frequency of the suspension system. So sometimes, not always, and be careful, but sometimes on a regularly bumpy road, it's better to go a little faster, because if I go so slow that I actually have the wheels going up and down at the natural frequency of resonance of the suspension system, then I have an exceedingly bumpy ride. So, two things from this. The basic principle of resonance applies to a child in a swing, and it applies to car suspension system. It applies to all suspension systems. Drucker suspension system. The mountings of the engines, all the construction of an aeroplane has to be designed so that we don't get resonance in the airframe or in the wheels, which would be very destructive. And now let's slow down. Just at resonance. Resonance. Absolutely necessary for any automotive engineer, any mechanical engineer, to avoid resonance in whatever they make. Same thing applies to buildings, a great big tall block of apartments. That has actually got a natural frequency of vibration. And if there is an earthquake which causes the ground to move at the natural frequency of vibration of the block of apartments, then the movement of the apartments gets bigger and bigger, and eventually the apartment block collapses. So even civil engineers who build buildings have to think about resonance. Mechanical engineers who build cars and planes have to think about resonance. So resonance is pretty important. But let's just look at a real car and say a few words about the suspension system. So here we are. I've persuaded somebody to bring their motor car along, and I've got my padlock and elastic bands. Now, I want you to remember, in order to think about the car, you have to turn this upside down. The padlock, a heavy mass, is the car body. And down here where my fingers are, these are the tyres. And the tyres, or the wheels, are connected to the car through a spring system. It's called the car suspension. And as you go over the road, bumps in the road make the tyre go up and down. And as we just saw, if the bumps make the tyres go up and down at the natural frequency of the spring system here on the car, at the natural frequency of the suspension, then your car is going to bounce very, very, very much indeed. But if you're going over a road and the bumps are rapid, then the car hardly moves. So the car is this, but upside down. So just to remind you, Rapid bumps, car hardly moves. Bumps in time with the natural frequency, and the car body goes up a very great deal. Now, there is something else in the suspension of a motor car which helps us as well, because we don't really want the car body to be going up and down too much. If I press down on the front of the car, and try this when you see a motor car, if I press down, the car goes down and it comes up again. And it doesn't bounce up and down. I can get it to bounce up and down a bit more if I can just detect the natural frequency of the system. But even so, it doesn't do it too much. Why not? Because in addition to the wheels and the springs and the car, you've got something else, a sort of cylindrical thing called a shock absorber. And what that does is dampen the vibrations. So the purpose of the shock absorber isn't really to absorb shocks, it's to dampen the vibrations of the car body. And one way of testing whether your shock absorbers need renewing or not is to go like this on the car, and if it bounces more than 1.5 times, you need new shock absorbers. This car just bounces once. The car's new, the shock absorbers are new, and so they're working perfectly well. You try it with an old car, and if the car goes bounce, bounce, you need new shock absorbers. So think about it next time you're in a vehicle. Think about the tyres going up and down on the bumpy road. Think about you and the car body, and in between these springs and the shock absorber. And if the wheels go up and down at the natural frequency of your car suspension system, you will have a very rocky ride and probably feel sick. Let's see if we can see the springs on a four-wheel drive. There's a bit more space, it's a bit more obvious. And very conveniently, a four-wheel drive car has just come in here belonging to BBS. Let's go and see the driver and see if we can have a look at his springs on his wheels. So now we've borrowed a Hilux from BBS, and this is particularly good because you can see very clearly here the wheels, the body of the vehicle, and then there, I'm not going to put my hand in because I'll get all dirty, there you can see the coiled spring which connects the wheels to the body. And as the wheels go up and down, that spring compresses and decompresses. And running through the middle of the spring, I don't know whether you can see it, but have a look on a real vehicle, you can see a tube going up through the middle of the spring, and that is the shock absorber, which, as I say, isn't really a shock absorber. What it does is dampen down the vibrations of the wheels so that not so much energy is transmitted to the motor car. So this simple elastic band and padlock, the basic principle of resonance, which is what happens when I move my hand in time with the natural frequency of this thing, the basic principle of resonance is really important when it comes to designing the suspension system of a vehicle. Because they have to design that spring system so that the normal natural frequency is not a frequency you normally meet on the road. Sometimes if you go on a very bumpy road, that principle breaks down, and that's where shock absorbers come useful, and that's why sometimes, but remember I said sometimes, it's better to go over a rough road a little quicker than a little slower, so that the wheels are going up and down at a much higher frequency than the natural frequency of the suspension system. So really what I want to point out is, I said at the very beginning of this program, science is child's play. And we started by looking at a child being pushed on a swing. Child's play. And we looked at the word resonance. And then we looked at other examples of resonance in sound. And a laser light works on resonance. And remember, MRI scanners in the hospital. MRI stands for magnetic resonance imaging. Nuclei resonate. And then we looked at the idea of every system having a natural frequency. Blow in the top of a bottle, you get a particular sound depending on the dimensions of the bottle. Natural frequency. And then my padlock and elastic band leading through the design of a car suspension system. And the same applies too with every sort of mechanical device. An aeroplane, as the engines wind up, there are lots of frequencies coming from the engine, and the design of the aeroplane has to be done very carefully so that there are no natural frequencies in the system of the aeroplane which could cause the aeroplane to self-destruct as the engines wound up. If you travel in an old car, you sometimes find at particular speeds your car is very noisy, and then go a bit faster and the noise disappears. Again, resonance coming in there. So really what I want to finish by saying is, science is child's play, but even child's play leads to some very, very, very complicated devices, ranging from the laser, through a car suspension system, through to many, many other sophisticated devices like magnetic resonance imaging. So remember, resonance, child's play, but leads to some very important ideas. I've got here a box of tuning forks. Anybody familiar with music will know that we use tuning forks to give us a very precise note. And if you pluck the forks of the tuning fork, you actually don't hear very much. But these little things are vibrating at the natural frequency of this tuning fork. To make it more audible, we do exactly what we do with musical instruments. Touch it to a wooden box which amplifies the sound. And different tuning forks will give us different notes because they are different sizes, the length of the vibrating portion. And so this allows us to get a whole variety of notes. And the natural frequency of oscillation of the tuning fork we can hear like that. Now, if I arranged to keep vibrating these electrically, then I would get this same note coming out all the time. It's called an electrically maintained tuning fork. So the noise would continue. Now, believe it or not, this is how we're going to use resonance to make an electronic watch work. Because some electronic watches actually have inside a tiny little tuning fork, just like this, but very, very small. And electrically, we make it vibrate. And the electric signal has to be just the right frequency, and we get resonance. The tuning fork in the little watch vibrates, and then this gives us the timing mechanism to make the electronic watch work. But the most advanced, or more modern, should I say, watches, inside here, you've got a tiny little crystal. And that crystal has a natural frequency of vibration. And electronically, and this is what the battery does, electronically, I cause this crystal to vibrate through resonance. And this gives the timing mechanism to make the electronic watch or clock work. And this crystal's natural frequency of vibration is very, very, very exact.
And so I will get an electronic watch, a simple, cheap one like this, which will be accurate to something like a 10,000th of a second, all through resonance of a tiny little crystal inside the watch, just like I can make tuning forks vibrate at their natural frequency. So resonance isn't only about pushing a child on a swing. Resonance, remember, has so many applications: the destruction of bridges, the basic principle on which your electronic watch works, the principle behind MRI in the hospital. In a previous program, we looked at an MRI machine, magnetic resonance imaging, because nucleuses of atoms, they have a natural frequency of vibration. And I can make the nucleus of an atom vibrate with resonance, applying an electric signal which causes it to vibrate, and that's the principle on which the MRI scanner works. Musical instruments all work with resonance. So remember, resonance, easily understandable by pushing a child on a swing, is the fundamental principle behind many modern devices. You know, when you tune in your television set or your radio, there is a little circuit in the television set which carries out not mechanical vibrations, but electrical vibrations. And when you tune in your television set, what you're doing is, with resonance, looking for the natural frequency of this little electric circuit in the television set. And that's how you tune in a television, using resonance. So resonance, like all of science, is all around us. And remember what I said right at the beginning: science is child's play.